New energy-efficient, compact fluorescent and LED light bulbs have been all over the media lately. It seems like every time you turn on the news or go online, you hear or read about the number of power plants that won't have to be built if everyone swapped out a few bulbs. You may have also heard that Walmart is implementing a new marketing strategy for compact fluorescents and plans to sell 100 million by 2008. One California lawmaker even believes enough in new bulbs that he's proposed banning incandescent light bulbs in California by 2012. But how efficient are these new bulbs? We at Alternative E have decided to figure it out by examining 3 different bulbs: a standard 60-watt incandescent, a compact fluorescent 60-watt equivalent, and an LED light bulb. To understand how efficient these new light bulbs are, we need to evaluate how much power they use. And to understand electric power, we need to make a short trip through high school physics. Electric power is the amount of energy transferred per unit of time and is measured in watts. The wattage of a light bulb is calculated by multiplying the voltage of the power source, which is measured in volts, and the current going through the light bulb, which is measured in amps. To examine these light bulbs, we built a device that will let us measure both the voltage of the power source and the current through the light bulbs. The device begins with a standard 110-volt plug, which leads into a switch. From the switch, the electricity is moved from the wires onto rails which allow the voltage and current to be measured. The white, neutral wire is attached to a solid rail, while the black, hot wire is attached to a split rail that allows the current through the light bulb to be measured. At the other end of the rails, the electricity moves back onto wires and into a simple light socket. Please note that this testing device is inherently dangerous. The electricity traveling through the exposed rails creates a high risk of electrocution if not handled properly, and there's a risk of burns from the light bulbs. We also need a multimeter to measure the voltage and current. However, it must be one that can measure AC voltage and AC current. To measure the voltage, we start with the device unplugged and the switch in the off position. We then place the multimeter in AC voltage mode and place the common probe in the neutral rail and the voltage probe in the hot rail, effectively putting it in parallel with the light socket. The device can then be plugged in. You'll notice that even with the device turned off, we're measuring a small voltage. This is a phantom voltage, likely due to electromagnetic interference or coupling, which shouldn't be a problem. When the device is turned on, you'll see the voltage jump significantly. If we zoom in on the multimeter, you can see that when the testing device was turned on, the voltage jumped from about 7 volts to 124.5. A voltage of 124.5 should be consistent for all 3 light bulbs, so we'll go ahead and enter it in the data table. To measure the current through each light bulb, we have to change the position of the multimeter. Now the multimeter is put in series with the socket, with one probe placed in the hot rail coming from the switch, and the other probe placed in the hot rail going to the socket. After the probes are placed, the multimeter can be set to measure AC current. Now we're ready to begin testing the light bulbs. We begin by placing a normal 60-watt incandescent bulb in the socket. The measurement from this bulb will give us a comparison point for the other bulbs. After we flip the power switch, we see the multimeter jump to 0.505 amps and hold steady. We add the current measurement to the data table and calculate the power usage of the bulb at 62.87 watts, which is pretty close to where it should be. Now we'll take out the incandescent bulb and put in a compact fluorescent that's sold as a replacement for the 60-watt incandescent bulb. When the compact fluorescent bulb is initially powered up, it measures in at 1/10 of an amp, but you'll see that over a few minutes it increases and settles in at 0.112 amps. Entering 0.112 amps into our data table gives us a power usage of 13.94 watts, meaning that the compact fluorescent uses 75% less energy than the standard light bulb, or, put another way, is at least 4 times more efficient. Lastly, we remove the compact fluorescent bulb and put in an LED light bulb. When we apply power to this bulb, you can see that the current measurement immediately jumps up to 0.03 amps and holds. After we enter the LED current into the table, we calculate that the LED bulb has a power usage of 3.74 watts, making it vastly superior to both the standard incandescent bulb and the compact fluorescent. Through our experiment, I hope you've gotten a better idea of the efficiency of some of these new light bulbs. However, we should point out one difference between the compact fluorescent and LED light bulb in terms of light output. A standard 60-watt incandescent light bulb has an output of approximately 850 lumens, and the compact fluorescent replacement has an output of 800 lumens, so it really can be swapped out with a standard incandescent in many situations. However, the LED light bulb only has an output of 60 lumens, and it was the highest output bulb we could find without going to a floodlight. So while the LED light bulbs use significantly less energy than other bulbs, they are not suitable for every application yet.